If you do every problem in this book, you will learn discrete mathematics. You learned discrete mathematics. Therefore, you did every problem. That progression feels intuitive, yet its structure fails to provide any mathematical certainty. It relies on a structural error that logic is designed to catch. In everyday life, whether you are reading an internet debate or sitting in a corporate strategy meeting, people use this type of broken reasoning to convince you of things that aren't necessarily true. Computer science tells us that if we want to spot these errors, we cannot rely on our gut instinct. Human intuition is too easily distracted by the specific words being used in a sentence. Instead, we have to look at language the way a machine does. We have to treat arguments as strict mathematical equations to find the actual truth. Stripping away the emotion to expose a lie requires mastering a set of invisible templates. In logic, these are called the rules of inference. Every logical argument has a specific anatomy. It is built from a sequence of statements called premises, which stack together to support a final statement called the conclusion. An argument form is only considered valid if the truth of all its premises absolutely guarantees that the conclusion is true. The Modus Ponens template states, if P implies Q and P is true, Q is true. Mapping real-world statements. Premise 1, the P implying Q. If you have a password, you can log on. Premise 2, the P, you have a password. By following the template, the inescapable conclusion is simply, you can log on to the network. Whenever an argument maps perfectly to this specific structure, the underlying logic is physically unbreakable. The mechanics themselves guarantee the final outcome. These rules handle massive amounts of complex information by drawing intermediate conclusions along the way. Take a scenario where your productivity dictates your physical state. First, we establish that sending an email is a prerequisite for finishing a program. Next, we note that if no email is sent, I go to sleep early. Finally, if I go to sleep early, I wake up refreshed. By chaining these together, the conclusion, if I do not finish writing the program, then I will wake up feeling refreshed, becomes a mathematical necessity. However, validity has a strict limit. It only measures the strength of the connection between statements, not the truth of the statements themselves. Consider this deduction. If the square root of 2 is greater than 3/2, then 2 is greater than 9/4. We state as our second premise that the square root of 2 is greater than 3/2. Therefore, 2 is greater than 9/4. The logic template functioned perfectly, but the conclusion is mathematically impossible. The starting premise that the square root of 2 is greater than 1.5 was false. A perfect logical machine fed garbage inputs will output perfectly valid garbage. To find the truth, verify both the mathematical form of the argument and the underlying facts. Which brings us back to our opening trap. If you do every problem, you learn math. You learned math, so you did every problem. This structure intentionally mimics a rule of inference to sound authoritative, but it secretly breaks the template. Instead of the P leading to the Q, it presents the Q first and tries to force the P. In logic, this is a specific type of incorrect reasoning known as the fallacy of affirming the conclusion. Common sense tells us why this fails. Just because the end result is true, you learned the math, does not mean doing every problem in that specific book caused it. You could have just watched a tutorial instead. By isolating the structure from the storytelling, you can identify a lie before you have even finished reading the sentence. By looking strictly at the underlying P's and Q's, you can see exactly where an argument's structural integrity fails. Let's test this skill. If it rains, the ground is wet. The ground is wet. Therefore, it rained. Drop into the comments and tell me, is this a valid rule of inference or a fallacy?